America, and this is my parachute engineering design project. The purpose of this project is to design and build a parachute that will land an egg safely with a terminal velocity less than 2 meters per second. Some vocabulary that is necessary to know when dealing with parachutes is terminal velocity. Terminal velocity is the point at which velocity or the speed of a falling parachute no longer is getting greater, so it's moving at a constant speed, it's not accelerating. The gravitational force minus the force of drag would equal 0. Drag is also important when you're looking at parachutes because you definitely want to make sure that your parachute slows you down. So drag is also known as air resistance. This is a force that is caused by air. The force acts in the opposite direction to an object moving through air. So as those air particles would hit the front of the object, it would slow down. So this is definitely important when thinking about a parachute because you definitely want your parachute to slow you down as you're moving through the air so that the landing is not rough. Throughout the course of this class, we learned that different factors that affect terminal velocity. So we did some experimenting and came up with a list of mass, area, gravity, drag force, and the density of the medium the object is falling through. How do you arrive at this equation? V squared equals 2 times mass times gravity divided by density area times coefficient of drag. We began with experimenting with some simple items. So we conducted 2 experiments, one to test mass and one to test surface area. We used a different amount of coffee filters and dropped it, found the terminal velocity to see if mass affected terminal velocity. And then we used different size balloons to test for surface area. Data from the coffee lab. So as the data shows in the table, as we increased the number of coffee filters, we also increased our average terminal velocity. So one coffee filter took less time to fall than 5 coffee filters. Here's the graphs from that experiment. So the graph on the left just basically graphs the terminal velocity versus the mass. So we're looking at that line, realizing that it would not go through 0, 0. So we need to linearize our data. And to do that, we needed to take the square root of the mass. Here's the balloon experiment data chart. So what we did with this is we blew up 5 balloons to different sizes. We used the string to find the circumference, then found the area of the balloon. And as the data table shows, as the area increased, the terminal velocity decreased. So this would be a good quality because as we get a larger parachute, that means that would slow us down and we would definitely not fall as hard to the ground. Here's the graphs from that experiment. So on the left is just the graph, the data that we had, terminal velocity versus area. But again, we're looking for the line to go through 0, 0. So we had to linearize our data. And we needed to find the linearization, we needed to have the 1 over the square root of the area. And then we graph that. So how do we get to this equation? Based on our evidence from the coffee filter and the balloon lab, we can conclude that mass and area do affect terminal velocity. So we need to combine what we know from these 2 labs. So we need to think about our units. We know that velocity is measured in meters per second. We know there's some kind of constant that we don't know yet. And we know that from the coffee filter lab that we had the square root of mass. And from the balloon lab, we had the square root of area. And so the units for that would be the square root of kilograms divided by the square root of meters squared. Besides mass and area, what other factors affect constant? Well, it is falling, so we would expect that gravity would affect terminal velocity. So we need to put that into our equation. So then we would have v squared equals the constant times gravity times mass divided by area. So what would the units for this equation be? Well, velocity again is meters squared divided by second squared. And again, we have our constant. Gravity is meters per second squared, and then mass is measured in grams, and area is measured in meters squared. Okay, so then we want to kind of solve for our constant to see if we can find any other relationships that could possibly affect our terminal velocity. So if we do go ahead and solve for our constant, then we're going to get that constant equals mass meters to the third power divided by kilograms. So based on the constant having the units of meters cubed divided by kilograms, that kind of looks like density. But density is typically kilograms per cubic centimeters or cubic meters. So that's why we're going to put that in the numerator. We can conclude that the density of the medium of the object falls also affects terminal velocity. So then we have velocity squares equals constant divided by the density of the medium times gravity times mass divided by area. Okay, so then we have meters squared divided by seconds squared equals constant divided by our units for density, kilograms divided by cubic meters, times meters per second squared times kilograms divided per meters squared. So to solve for this, we want to try to get a variables we want to try to solve for the constant. So we want to get the constant on one side. So we need to go through all these different variables. So the first thing I would probably do is multiply both sides by meters squared. So then we would get meters to the fourth power divided by seconds to the second power equals constants divided by kilograms per cubic meters times meters divided by second squared times kilograms. So the next thing I would probably do is multiply both sides by kilograms per cubic meters. And then you're going to end up with kilograms times meters to the fourth power divided by cubic centimeters times second squared equals the constant times meters divided by second squared times kilogram. Okay, so the next step I would probably take is to multiply both sides by second squared. And then you're going to end up with kilograms times meters equals constants times meters times kilogram. And then you're going to multiply both sides. Okay, no, sorry. And then you're basically going to get down to the end of the equation and you're going to realize that kilogram equals kilogram. So basically the constant has no units. So how does a parachute reduce terminal velocity? Okay, so when you use a parachute, you have a larger surface area, which will lower your speed when falling. So parachutes decrease speed by increasing the surface area. So our next step was to think of some parachutes that we might consider making. So here are my sketches of my parachutes. My sketch 1, I had a square parachute with 4 strings. Sketch 2, I had a round parachute with 8 strings, and I decided to cut my strings about the length of my diameter. And then my sketch 3 is I had 8 strings and I doubled the length of the diameter for my strings, and all 3 sketches included a ping pong ball for my mass. So here are my 3 prototypes, my square parachute, my round parachute, and then the parachute where I doubled the length of the strings. So I did a little bit of an experiment. I just kind of threw these off the back of my deck to see which one would work the best for my prototype. So I had for parachute 1, which was my square parachute, was a terminal velocity of 1.7. Parachute 2 was the round with the strings the size of the diameter, and I had 1.66. And my third parachute was the round parachute that had the same area as number 2, but the strings were double the length. So based on this data, I decided the best design to build would be my round parachute with 8 strings, with the strings about as long as the diameter of the parachute. And I decided this because it had the smallest terminal velocity. So the next thing, we have to implement our solutions. So I needed to build a prototype using what I found out through my experiment. So we need to go back to that formula for terminal velocity. V squared equals 2 times mass times gravity divided by density times area times coefficient of drag. Well, I can fill in some of those numbers because I know them. I'm just going to assume that the velocity is 2 because that was kind of like we were supposed to have a velocity of 2 or less. And then I found the mass of the ping pong ball to be 0.00248 kilograms. And then, of course, gravity is 9.8 meters per second squared. I went on the internet and I looked up the density of air, and I found a value of 1.22 kilograms per cubic meter. I do not know the area, and I'm just going to put in a value of 1 for coefficient of drag, just so I can find some areas to test. So by this, the next step is I solved this, and I found that the area of my prototype should be 0.001 meters squared. So here's how I found the round parachute's prototype coefficient of drag. Now, through some mistakes of my own, I meant to have a area of 0.001, but my actual parachute ended up being 0.0227. So with that information, I went ahead and used the formula to find out what the coefficient of drag was for my parachute, and I found the coefficient of drag for this parachute to be 0.64 meters per second. So now I need to use that coefficient of drag from my prototype to build a parachute that I'm going to actually land an egg safely with. So again, I'm going to use 2 meters per second for terminal velocity, and I'm going to use my newfound value of 0.64 meters per second for the drag coefficient to find the area of the parachute I should build. So I put in all the numbers that I knew. So I have velocity squared equals 2 to the second power equals 2 times 0.04784. That would be the mass of the egg that I'm going to try to land, times 9.8 meters per second squared, which is gravity, divided by 1.22, which again is the density of air, times the area, which I'm trying to find, times the new coefficient of drag that I found from my prototype, which is 0.64. So after calculating that, I found that I needed to have a parachute with an area of 0.30022540983, and that should say actually meters squared. So now I know the area of the parachute, then I can find the radius of that parachute. So I put in 0.30022540983 equals pi r squared, and through that I found that the radius of my parachute should be 0.31 meters. So throughout this course, we had discussion boards, and those have been very helpful because when people post things, it gives you things to think about, or maybe you have a question and they can help you answer it. Unfortunately, I had to send lots of emails to my professor because I was not catching on to the material quite as fast as I wanted to. Also, I communicated through emails with my classmate David, who was also in this class, and I also made a couple of visits to UC to get help with Tracker. So here is my final parachute that I released over the edge of the mezzanine at my school. And here's the tracks that I made from my flight. So if you look at the position time graph, which is the top graph, you can see that this parachute did reach terminal velocity, and I can tell that because the line is fairly straight. This is a graph of the velocity, and it's got a straight line through it. So basically what I wanted to look through here is what was the mean velocity of my parachute as it was in its flight. And I found that the velocity of my parachute from this, as you look at the statistics to the side, I had a velocity of 0.78 meters per second. So my predicted terminal velocity was 2 meters per second. I actually got a velocity of 0.78 meters per second. So possible explanations, human error. I did have some math calculation errors that I found later. And I think the coefficient of drag error for the prototype is probably part of the problem. So that concludes my presentation on my engineering design project of parachute.